My name is Rob Chambers. I'm the Director of Hopes and Dreams at Lockheed Martin in Exploration. Official title is a Director of Strategy for Exploration, and that includes our human spaceflight activities, Orion, obviously a lot of folks know us for, all of the work that we're doing to get humans to the moon and to do things on the moon, all of our robotic space exploration activities, including asteroids and Mars and Venus and so forth. And then because exploration begins at home, we also have earth science and weather, climate intelligence, and space weather as part of my little group. Thank you so much for joining our panel today. My esteemed colleagues from across the world, actually, thank you so much for joining. What we're going to do is to talk a little bit, and each of us will go, and then I want to take your questions. I have questions. I already know the answers to my questions, so I'd rather you ask questions that we don't know the answer to, which will be much more exciting. Usually I'm the one that has to answer them, but as the moderator, I don't. And so I welcome the hardest questions possible, please. In July, I guess, was Ascend in Vegas. On the Lockheed Martin side, we rolled out what we called a water-based, nuclear-enabled water-based economy, a vision, if you will, for not guaranteed what the moon is going to look like and not what Lockheed Martin is going to do on the moon, but an existence proof, if you will, where the math works with all of the piece parts and how they would be tied together to have I would call it a self-sustaining to a large extent group on the moon actually doing useful things. So we're going to talk a little bit about that in a moment. One of the things in Vegas that we talked a lot about was this was not Lockheed Martin's vision. We threw it out there, but we want it to be everyone's vision. We want folks to see themselves in this and give us feedback. We can be the custodians of the novella and the simulation. If you haven't seen the simulation, you can go drive a rover in our booth, if you can find it, over in North Yellow Hall 3. But you can drive a Lunar rover. Yes, there is a ramp that you can jump with the Lunar. Like, how can you have a 1.6G driving sim without a ramp? So there's also a lot of serious stuff in there. There's also, and this sounds like a sales job for Lockheed, so let me just get past this part and we'll get to how this is actually not all Lockheed. But there was a novella we wrote for which Lockheed, I think, is on the front and the back page, and that's it. It's all about you, written in the first person, very non-big aerospace company format of how you are a contractor on the moon maintaining these systems. And again, it's not because those are exactly the systems, but it is a representative set of systems that allows us to move from talking just architecture, which NASA and the other agencies have done a fantastic job laying out as part of Artemis and folks buying into the overall construct with the Artemis Accords. But now let's actually get into the nitty-gritty and start talking about how, you know, the US rovers and Canadian rovers are going to have the same wheels, so we can put each other's stuff up on blocks and borrow a wheel if we need to, which Laurie and I have talked a lot about. Will be a fascinating policy question. But in all seriousness, talking about how these piece parts are going to play together, I think there's been, from my perspective at least, a lot of what looks like random acts of engineering. And then you've got this architecture, which is very well thought out, but we haven't had a lot of dialogue about what it looks like in between. And so that's the objective. So I really want to thank my teammates now or colleagues from across the world, from MDA and Tassi from BWXT back in the States, and from Rolls-Royce in the UK. So we're going to talk through, each of us, a little bit on our vision. And again, do we need to put up the QR code for the questions? I forgot to ask that. Oh, you did? Okay. Does everybody have the... All right, take your phones out. Snapshot. 10 demerits if we don't get really awesome questions from you all. We want like the full decay path for uranium-235. Jake offered to do that. Okay, let's hop back. Okay, so just a couple of things. Here's where you can download the novella. You can swing by and pick it up as well. The pieces that we foresee of a self-sustaining initial small number of people, but a lot of robots that are actually producing enough power to be able to produce enough water that feeds into a infrastructure economy. I'm going to talk about that in just a second. And so you'll see on the bottom, fission surface power. There is a need for solar power at the moon, but that won't cut it. Right tools for the job. So you need both solar and nuclear for reasons that we're going to talk about today. Habitation, we're going to talk a lot about. We probably don't have enough pictures. Well, this is a plug. I need models from everybody to throw into our sims because we didn't want to get sued, so we just put in what we could find publicly available, and in some cases, that was kind of our stuff. But we would love to start showing other folks' systems. So we're going to have Roberto talk a bit about habitation. Tazi is really the world leader at this point for cislunar habitation, I would say. So that's there kind of in the middle part. Over on the right, we're going to talk just a little bit about, probably I will, from an ISRU and water production perspective. And I want to differentiate different kinds of infrastructure in just a second. So let me go to that in just a moment. Actually, I guess I'll go back. Last thing I'll talk about is cryopropellant management and processing. So there'll be a lot of miners, but there'll probably be fewer refiners, if you will, where that water can be processed, cracked, and then either used on the surface or launched as water, cracked on orbit, depending on the use case. And then the last piece, just to tantalize you on the upper left there, why would you use the water that you harvest to burn as liquid hydrogen oxygen to get the water up to orbit? You actually use 4 kilograms of water for every kilogram you get on orbit. So our thought process is once you have nuclear power, thanks to our esteemed colleagues, once you have the mobility and enough habitation and systems to support the people to run all this, you might as well use that nuclear power to electromagnetically launch that water up into orbit. So we won't talk much about that today, but just to kind of round out the overall picture. We see at sort of this time frame, things are going to be easy to get into low Earth orbit. I think we all would agree things got a lot easier to get into low Earth orbit about 2 days ago. Astounding feat of engineering. I keep watching the chopsticks. It's pretty awesome. So what we haven't as a world, as the human race, figured out is how we're going to move things from LEO outward, and then what should the role of the moon be. And so as we talk through here, we all see the moon as almost a port of call, if you will, and the moon as a location either in orbit or from resources on the surface to go on out to Mars. The last thing I'm going to just acknowledge is we talk a lot about water production in some of the stuff Lockheed has brought forward. Water is not a marketable product Earthlings will pay for. If you have the astronauts there to find the water, to then crack the water using nuclear power to drink the water in order to go find more water, that's what we in the US call a self-eating watermelon or a self-licking ice cream cone. That is not an economy. There is no lunar economy unless there is Martians or rich aliens on the far side. It's an Earth-Moon economy. So we're going to talk a lot about infrastructure today, but don't confuse that with whatever marketable product y'all are going to pay for. And my kid who pays for internet access, well, he doesn't pay for anything. I pay for his gigabit a day internet habit that he has, and I'm actually helping to pay for a large fraction of, I think, the LEO communications market. We don't have that at the moon yet. And so I don't know what that's going to be, but don't confuse water with a marketable product. And so I want to acknowledge that. So at this point, that sort of sets, I hope, a little bit of the framework. In the time that we're going to talk about here, we've got a few dozen people on the surface of the moon. We've got an infrastructure. How do we get there? What are the systems being developed today from across the world through a variety of companies? And what does that future look like? So with that, let me hand it off to Laurie Chappell from MDA.
Test. Hi, I'm thank you. I'm Laurie Chappell from MDA Space. I'm the Senior Director of Business Development at MDA. So for anyone who's not heard of MDA Space before, we're a 55-year-old company headquartered in Toronto, Canada. And we specialize in 3 different business areas, which are Earth intelligence, satellite systems, and then the robotics and space operations business unit. So I'm from robotics and space operations, the most fun one. I'm poking at my colleagues. The most fun business unit. There we obviously focus on robotics. So this is a chart we have a long history in doing the space robotics, mission-critical space robotics that interact around humans. So you would know us from the robotics on the space shuttle, the robotics on the International Space Station, and now we're moving out to the moon to do Canadarm3, which is the robotic system for the gateway. So that's sort of the landscape of our robotics heritage, going from low Earth orbit now out to the moon, and as we glom onto the novella, or Rob's vision of what do we see as we now move towards the surface of the moon. So obviously we're biased, so you'll see robots covering everything in this picture. But there's a big focus on, like as we do at the International Space Station, we're doing logistics, like we're taking cargo vehicles that arrive, thank you, Roberto, that arrive at the space station, transporting payloads. There's a whole infrastructure and supply chain that we're used to dealing with at the space station, and now we anticipate dealing with on the surface of the moon. So you'll see in the picture the mobility. So like when the landers come and show up, and there's the power, the habitats, everything. There's a whole supply chain that needs to unload the landers, get the socks and shoes and toothpaste somewhere to the habitats, build the habitats. So that's what we're focusing on now. We're starting to work on the robotics as part of the Lunar Dawn LTV team. So that's the first piece of it, and I think we'll probably talk more about Canada's vision for the rovers going forward. But now I should hand off to Roberto.
Before I leave that picture, we assume that the guy on the lower right is actually not a human, it's just an android.
Yes, that's right.
Okay, yeah.
Yeah, you don't need
Called your
humans.
bluff. Yeah, the spacesuit is just to throw us off. And you mentioned actually surface logistics. So NASA currently has Appendix R, for anybody not familiar with that, which is focused on complex lunar logistics. What happens when you get something to the surface? What do you do with it at that point that prevents us from spending so much human time to unload? So.
And that's what I love about the novella. Like, it's taken all these pieces that seem like they're independent, and then told the story of how they work together, and thinking through that chain.
So Roberto, ciao.
Good morning, ciao. Roberto Provera, I'm the Director for New Initiatives, Partnership and Innovation in Thales Alenia Space, Exploration and Science. Basically, it's a long name to do our hopes and dreams office in Italy. Thales Alenia Space is a joint venture between Thales and Leonardo. We formed the so-called Space Alliance with Telespazio, and we are the manufacturing leg of the alliance. And especially for exploration, where I work for, I think we have a name in pressurized elements for human life in space. Our heritage starts from before the International Space Station. We developed several elements for the International Space Station, and we are still supporting the space station life with the cargo vehicles. We developed the pressurized cargo module for Northrop Grumman, and from that heritage we went to be an actor for the Lunar Gateway, in which we are developing again several elements, both for at commercial level with Northrop and the Halo, and for the European Space Agency. And now the next step is to start building the infrastructure on the moon. It is in order to be sustainable, we believe we will have to have a set of infrastructures on the moon. Of course, as you say, you are in your pictures, you see a lot of robots. We see a lot of habitats, and I think they complement each other, I believe. And The good news is that this is not just a picture, because lately, in the last couple of months, Italian Space Agency passed, and NASA passed the MCR, the Mission Definition Review for the multipurpose habitat, and that's a great step, because through that we will be able to start the development of the first human outpost on the moon. You see that there are some wheels on that, because at least we have to move from the lander, not to be polluted. So we will have some mobility. There's room for anyone, I think, on this project. We plan, therefore, to start the development 2031, 2032, the delivery to the moon, and of course, it's a big step in technology. Because from that we have to change our design in order to be sustainable on the lunar surface. It's very quickly. I took a lot of time to speak, but again, on the infrastructure side, we will have to be sustainable. We will have to have a logistics chain that will be able to support the operations, and we are developing the European cargo lander, Argonaut. The capability is about 2 tons for delivery cargo to the moon, and that will be integrated in the overall logistics support of the various agencies. Again, in terms of infrastructure, we think that communication navigation is an essential part, and together with Telespazio, we are running a program for it's called Moonlight. It's to serve users for communication navigation on the moon. All this is served by a lot of energy, a lot of this type of infrastructure needs to be supported, and in the far future, I've already started some concept, the solar-based power systems as a piece or a brick of the overall scenario.
Great, thank you. You know, my daughter just graduated from college, and she's moving into a house, and I said, you know, what you need is the same stuff we need at the moon, which is electricity, water, cable, family car. We talked through all of that just now, but I said, you know, if you're a Purdue grad, you also need a nuclear reactor or maybe a rocket in the backyard. So that's where we stretch it a little bit further from an analogy standpoint. But Kate Kelly from BWXT, over to you.
Thanks, Rob. So my name's Kate Kelly. I'm the Director of Space and Emerging Programs for BWX Technologies. We are a new company to, I think, the space industry, but we have a 150-year legacy of supporting energy generation and delivery across multiple domains. We are an 8,000-person company with most of our workforce between the US and Canada, and we're most known for 2 main missions that we have many decades of supporting. The first is delivering the nuclear reactors and plant components to power the US Navy's submarines and aircraft carriers, and then also delivering the plant components and servicing many aspects of the Canadian nuclear utility fleet. So it's those 2 missions where we are providing and have a history of providing reliable, resilient, efficient energy across the US, across Canada, and more globally than that. Over the last several years, the US and across the globe have been pushing to deploy nuclear energy across multiple new domains. So we have a long society, uses nuclear energy reliably. Often you probably don't even see the benefits that you're receiving from it. But there's been a push to harness that energy in new places that are hard to reach, or in new ways to help us achieve a more carbon neutral energy sources. And so as we were looking to combat climate change and sustain a presence in some of these hard to reach places, the subsidiary that I represent today, Advanced Technologies, was born. And so we'll talk about some of the main areas and our focus areas, because they're all related. And while it's not space specific, it's all helping us push this mission forward of getting more reliable energy, higher power capability in space. So we have three main focus areas. The first is terrestrial defense. So we're working on a prototype project to deliver a microreactor and test it within the next couple years. There's hardware, there's fuel that exists, and that project is underway, and it'll be a huge step forward for the US in being able to better support the US Army and have more robust energy needs. We're also pursuing commercial variants of that, so looking at how we can achieve or deliver tens of megawatts of power to help create more sustainable electricity for industrial applications, places in very energy and electricity in very hard to reach places where you might not have reliable energy sources. And then we're also looking to apply this in space. And that is the division that I lead. I'm going to show a picture of, so Rob showed the future for a collaborative lunar-based economy and environment. I'm going to show our future for space nuclear and what that looks like deployed. What we envision is using nuclear power across multiple different applications. So whether that's radioisotope or fission power, whether it's nuclear energy for to provide electricity to operate a spacecraft, operate a lunar lander, or for enhanced propulsion capability to get places further in space faster than we can using existing technologies today. And as we look forward to what does this path to deployment look like, the first step in that process is to demonstrate the technology at a relevant scale in relevant environment. And regardless of whether we're talking power or propulsion, I think that's a huge step towards deploying this future architecture where we have enhanced capability across various places within space and beyond. So one of the Pathfinder projects right now that is working towards that development is a project called Draco. So it's the demonstration rocket for agile cislunar operations. It's a collaboration between the research and development branch of the Department of Defense and NASA. And it's a project that BWXT is thrilled to be a part of, delivering the fuel and reactor to our partners, Lockheed Martin, for a flight test within the next couple of years. And so that will be a huge step forward for the deployment of space nuclear technology. There's flight hardware that exists today. It's very real. It's a very doable feat to demonstrate nuclear thermal propulsion on orbit in the next couple of years. That will set the stage for the deployment of other nuclear technology. So we're looking at nuclear electric propulsion through some partnerships with the US Department of Defense and the Air Force Research Laboratory. And then we also have several pursuits related to the deployment of nuclear reactors on the surface of the moon. So developing the key technologies that allow us to take that step forward to demonstrate at scale and then ultimately deploy multiple units of these systems. And so we're collaborating with Lockheed Martin and participating on NASA's fission surface power, but then also looking beyond that. And so working with my colleague to my left with Rolls-Royce Submarines Limited to support some of their pursuits with the UK Space Agency. So it's a collaboration. I think there's collaboration required across the deployment of all of these applications, but that's that collaboration, I think, that makes this ambitious future achievable in the near term. So with that, I'll hand it over to Jake.
Thank you very much. Thank you, Kate. Yeah, good morning. Good afternoon, nearly. Everybody, yeah, so my name's Jake Thompson. I'm the Director of Novel Nuclear and Special Projects at Rolls-Royce. I also have the honor of being a Kármán Fellow this year. So I do urge you to go and look at the Kármán project. Fantastic work that they do. So Rolls-Royce is not a name generally associated with space. We're a power and propulsion company. We provide power and propulsion across land, sea, and air domains. gas turbine technology and nuclear technology. So a little bit like Kate said, Rolls-Royce for the last 60 plus years has provided all of the nuclear reactors for the UK's Royal Navy submarine fleet, and we collaborate with our colleagues and friends across the pond in BWXT as well. We're now taking that expertise both from our aerospace gas turbine capabilities and our nuclear heritage and applying that to the space domain for all of the great reasons that Kate's just said. And it's my privilege to be leading that effort in Rolls-Royce. So just a snapshot, really, and it is a snapshot because this is actually a still taken from a video of kind of our vision of what the future human presence and lunar economy might look like. So I do urge you to come down to the UK Space Agency Pavilion downstairs and actually see the whole video and come and talk to us. And we've also got a model of our microreactor on the stand. And I think I don't really need to dwell too much on this slide because this fantastic panel has done the work for me. Everything that we're going to need to do on the moon, not just to survive, but to thrive and to explore, is going to need power. It's going to require power. And as Rob said, solar plays a part in that, but there's places, interesting places we want to go that are permanently shadowed. So that's one reason, and there are many, why we will need nuclear power as part of that lunar infrastructure and that lunar architecture. And we, as Kate said, want to apply our nuclear expertise in a very similar parallel environment, submarine reactors, take that capability and apply that to space nuclear. So I just wanted to sort of, and this is my last slide, and I guess we'll go to questions then. I just wanted to bring it back to, well, what are we doing today to make that vision a reality? Because the videos are fantastic, you know, and the Novello, etc. But how are we going to get there? And there's work going on in all our companies to turn that vision into a reality. So just some pictures here. We've been greatly supported through the UK Space Agency over the last about 4 years. To turn that vision of space nuclear into a reality. And it's turning into hardware and test hardware as we speak. So the picture, the kind of picture on, which side is it? The right-hand side, that is taking our turbine capability in Rolls-Royce Group and developing a closed-loop Brayton cycle. So that takes the hot gas that you generate the heat in the reactor, heater gas, and take that hot gas to drive a turbine to generate the power. So we're developing that technology and demonstrating that technology, as Kate said, at an applicable scale. We've also been doing some manufacturing trials and some tests on other aspects of the reactor. And if you want to find out more, please do come and see us at the UK Space Agency stand. And then just you can't read the words, but the kind of 1 to 10 on the bottom side there. So I said at a panel this morning, like nuclear is hard and space is hard, and together they're really, really hard. So we're working on a collaboration effort with our colleagues and friends at BWXT to really understand the kind of design envelope for space nuclear, make sure we're developing systems that are scalable and robust and will meet our future demand and aren't just a kind of spot point design. So through the UK Space Agency International Bilateral Fund, we're collaborating with BWXT to really explore that design space. I'll leave it there. Thank you.
All right, awesome. Thank you. You guys are doing great. Your questions are much better than mine, so we're going to go with yours. They're much harder, so buckle up. Speaking of buckling up, extrapolating from rovers back to arms, could you tell us a little bit, Lori, the robotics, including the human cyborg that you showed in your picture. By the way, I noticed, and we didn't plan this, every picture showed more and more capability set. So sometimes good things happen to all of us. So that was actually pretty cool how those pictures turned out. But early on, we're not going to have humans there all the time. Can you talk a little bit? You and I actually, you mentioned the other day, autonomy versus automation. And there actually is a pretty significant difference between those. You want to share your guys' thoughts on that?
Sure, and I guess we've seen this grow over the course of time. starting out with the space shuttle. There's some people from the space shuttle team in this audience actually, where the robotic operators were actually looking out the windows of the space shuttle to like check for clearances, and they're on joysticks, hand controllers. As we moved to the space station, doing the logistics with Roberto on the space station, that moved from the astronauts in the space station controlling the robotics to it's almost exclusively controlled by people on the ground doing the robotics, and it's not joysticks anymore, it's like automatic commands. So the robot isn't thinking, but it's saying like go from point A to point B and following a very deterministic path. As we move to the Canadarm3 for the Lunar Gateway, we're going from the automatic to autonomous, so introducing levels of autonomy where the person doesn't need to intervene. You can give it a high-level complex task, and the robot will go do that independently. And then obviously that translates to the lunar surface where like at first the astronauts are going to be there for like a week, a month at a time. So these systems for the rest of the time do need to be autonomous. So we're developing autonomy for the lunar vehicles, not only the robotics, but also autonomous self-driving car technology. So you can see that that progression, and at least on the moon, we'll start from day one because it's mandatory.
Awesome. Hal, please open the doors, is all that comes to
That's
mind.
right.
Nothing can go wrong. Let's see. So this is just in random order to keep you guys on your toes. So Jake, one of the folks asked a question, which is a good one. Can you, in 239 words or less, radioisotopes versus fission power? Because a lot of folks, when they think space nuclear, probably think RTGs. So just
okay, 239 words. Those words didn't count. Okay, yeah, so very quickly, and Kate, please chip in. Radioisotope power systems are based on an unstable isotope, and that unstable isotope basically decays on its own into daughter products, and that decay produces heat. So those daughter products are vibrating around, and they get quite hot. So things like plutonium, americium, strontium, all materials that decay naturally and produce heat. And then a radioisotope power system basically takes a lump of that material. This is over 239 words, but we'll go with it. Takes that material and sort of wraps a system around it to directly convert that heat into electrical power. Generally fairly low levels of power. So kind of 10 to 100 watts, that kind of range. Fission surface power, nuclear reactors for space, are just like nuclear reactors here on Earth. They take uranium and they split that uranium atom, so fission that atom, and then that produces quite a lot of heat. But it also produces neutrons, and those neutrons go on to split other atoms, and you get a controllable chain reaction, creates a lot of heat. That's a fission reactor using uranium as a fuel. And then we convert that heat into, or you transfer that heat into a working fluid, gas usually, in these systems. And then that gas is used, as I said earlier, to drive a turbine to generate electrical power. In power terms, much bigger systems, tens, hundreds of kilowatts, but scalable ultimately, especially with heavy lift, to potentially megawatt class reactors in the future.
Awesome. That was 239 in metric, I think. So. English. Let's see. Okay, we're going to come back to nuclear in just a moment. So, Kate, buckle up. Micrometeorites and meteorites and orbital debris and so forth. We think a lot about that from an ISS perspective. But interesting questions here, both from a lunar orbital standpoint, Roberto, and then what thoughts have you guys had on surface debris and any accommodations you're going to need to make there relative to what you guys do on orbit when you think MPH?
First of all, the environment of low Earth orbit in terms of debris and micrometeoroid is worse than the lunar orbit environment. So, and I think it's one of the few points in which we are lucky for when you go to the moon. So, in terms of debris, lunar orbital orbiting elements will be equipped, of course, with micrometeorites. But the challenge there will be the dust. For both the gateway, with the lander that will human lander that will dock to the gateway, and of course when we speak of habitats or elements on the moon, the real challenge is the dust rather than the micrometeoroid. There are several technologies that can be applied for that. There is some basically. We are testing now. We have some means to discharge with the electricity the lunar dust in order to keep it and then remove it. That is a bit far, but it's a challenge that we are facing now. And the other point in terms of environment that is a big difference with respect to the low Earth orbit is the radiation. Of course, that is another point that we have to tackle when we think to a permanent presence on the moon.
Can I add?
You may.
Tying the autonomy question together and the micrometeoroid, on the space station, like our robotic systems have been hit by the micrometeoroids, and like the Canadarm2 actually has a small hole in it that the team found by doing manual inspection, which is a routine thing. So now our team of crack engineers has tied in the autonomy by they've developed a tool that will autonomously scan the systems that we have and identify the actual strikes. So instead of having a human like poring laboriously over the equipment and doing all these inspections, you can just tell the system autonomously to go inspect the system, and it will come up with a report that says, here's where you've been hit and you need to go look at these areas. So autonomy is everywhere.
Let's see, going back to nuclear, Kate, so Jake did a great 239-word explanation, kind of from a nuclear power perspective. Can you talk a little bit about Draco and just the basics of NTP, and somewhere in there talk a little bit about HALEU versus HEU, because I think that's one of the major enablers for being able to move us forward to this vision in the future.
Yeah, I'd be happy to. So I'm going to make this as basic as possible, because I am by degree not a nuclear engineer, not even an aerospace engineer. I'm a chemical engineer, so I had to learn, all of this. But so for nuclear thermal propulsion, we talked about how you can take nuclear fission and convert that to electricity to power a spacecraft or a lander. This is using that same fission chain reaction, but instead of converting converting that energy to electricity, we're converting it to thrust. So an NTP reactor is a very fancy high temperature heat exchanger with a very extreme difference in temperature between your cool, very cold propellant and your very hot reactor. And that change in temperature as the propellant gas expands through the nozzle creates this massive amount of thrust and an efficiency 2 to 5 times greater, depending on the mission, compared to chemical propulsion. So that can be a huge enabler for cislunar transportation. It can be an enabler for reducing the mission time to extend human exploration from the moon to Mars. And it can be done in a way that with technology we know we can make and we know is going to work as planned because of a lot of advances in testing and how we can model and build these systems. One of the big advancements or enablers to the Draco demo was actually some policy change in the United States. So when we talk high enriched uranium compared to high assay low enriched uranium, it's talking about the percentage of that fissile isotope that's going through that fission chain reaction. So the higher the percentage, the more of that isotope there is, and the more efficient the heat that's generated through that reaction is. And now with a high assay low enriched uranium system, you have 1/5 by comparison the amount of fissile isotope, but you also we're in a more favorable non-proliferation state because of the use of that material. So it's more enabling, it's simpler from a policy perspective, which is one of the major challenges that we need to work through, is just exercising our policy and exercising our regulatory process to go through the safety review prior to launch to know that we can safely and ethically operate these systems and deploy them on orbit. So that is a change. So I talked about policy changes in the United States that simplify the process to launch a high assay low enriched uranium system. So it takes away some of the levels of approval that would be needed and review. But it is a technical deviation from the baseline development that's been done extensively by the United States. So the United States space nuclear is not new. We've even launched reactors in space. Other countries have as well. We launch radioisotope power systems into orbit all the time for various deep space and science missions. What's new is going through this process with this HALEU reactor because it just deviates from the base knowledge that we have and that we've gathered over 6 or 7 decades of space nuclear development.
Yeah, we talk about the Draco program in particular being DARPA hard. It's kind of for a couple of reasons. One, we're gonna take it critical after we are up in orbit safely at a high altitude, such that the decay of the orbit due to drag is many, many times longer than the orbital decay or the radioactive decay of the isotopes. So doing it on orbit for the first time without that ground test is DARPA hard. And it's also hard because of the policy. Some of my colleagues in DC say that policy engineering is harder than hypersonic guidance engineering and harder than nuclear engineering. And there are days when I agree with them. So that's the other thing that these pathfinders are doing, and there are several questions about that, which is how do we do this safely, ethically, responsibly in order to literally propel the human race forward. So let's see. So these systems will be large, will be massive, and will be heavy even with 1/6 gravity. Still, the weight will still be high. Can you talk a little bit, Lori, on from a Canadian perspective, and you're not speaking for Canada, but Canada has talked about doing a utility vehicle now that would be a key part of the overall infrastructure for when we move, whether it's water or hydrogen or oxygen or small nuclear power plants. What do you guys see? What does Canada see as part of that part of the contribution for Artemis?
Sure, and you would have seen, if you have your finger on the pulse of the Canadian space community, you would have seen the Canadian Space Agency announce what they're calling a Lunar utility vehicle. So that's Canada's next contribution to the Artemis mission. And how it's envisioned is that it's uncrewed rover that will support logistics and other medium-size payload transport on the surface of the moon. So complementary to LTV, which is the crewed vehicle. The lunar utility vehicle will probably be in that class, like the 1,000 to 2,000 kilogram class, and will be used to support the humans. So if you saw in Roberto's pictures, there's a lander, there's a robot, nice, and it's taking all these payloads off, and they're like sitting on the ground. They need to go somewhere, so you're not going to spend time with humans like dealing with all of this cargo. Like the lander comes and all the cargo, the lunar utility vehicle can take that cargo, transport it to the habitat, dock to the MPH, transfer pressurized cargo, all of those sort of things, while also doing other support tasks like hooking up the nuclear systems. Like you have a power plant, you need to plug it in somewhere, there's cabling. A lot of support and infrastructure tasks that just really support the infrastructure noted in the novella that enable the sustained human presence on the moon. That's where we're at. We've just, we're doing a small study of that right now, and it's pretty exciting.
That's awesome. So we'll have to get those systems to the surface, Roberto. That we, of course, on the American side of the pond, we've got the CLIPS missions, which are working their way through and working to larger payloads. Then we've got the plans for what we call the human class or human scale logistics associated with the HLS and SLD programs on the very, very high end. But what has not been afforded or created yet is sort of that middle ground, and that's what Argonaut is focused on. You want to talk a little bit about where y'all are on that?
Sure. ESA selected Thales Space recently for the development of the Argonaut. We are closing the negotiation with ESA. Hopefully, we will be ready to start by the end of the year. Argonaut is a lander that has an initial capability of, I would say, up to 2 tons. That is, I think, fitting with what you are planning to do with your LUV. It's a challenge for Europe because it will be the first time Europe will have such a system. So it is in the line of European development of European capabilities and integrating the capabilities in an overall Artemis architecture. The first flight is planned by 2031. Our hope is that while we will demonstrate this capability, we will be able also to grow the capability of in terms of mass up to 4 to 5 tons. Of course, that will require some modification and some maybe a dual launch because as Europe we have Ariane 6 that is serving this, so we will have maybe to do with 2 launches. It's a challenge because basically a lander is a set of engines and GNC. So quite interesting technology in the 2 cases, and we will select the engine by the end of this month, and then we will proceed for the final negotiation with ESA.
It's really exciting. In fact, that's one of the points we should highlight is all of the things that you see in the picture there are under some level of development today. It's not science, it's not science fiction, it's science fact, but seriously it is. These are all systems, and they're not just all in one country, much less all one company. Let's see, so we're gonna enter our speed round. Is you only get 2 words for the answer for each. Up to 5, I'm gracious, I'm wise and benevolent. Up to 5 words, what keeps you up at night in your areas associated with CEST Lunar? Lori, go.
Interoperability. So
actually, that was almost 5 syllables. I think it was more like 6. But no, you could even use more words. But yeah, say
like how all these systems are going to plug together. So what is the USB port of the moon?
Yep. So we can make sure we have the same tires, so we can steal each other's tires and leave each other up on regolith blocks. Yep. Okay, Roberto.
I think a common vision shared for standards.
Wow, that's good. Yeah, that the common vision piece, and that's why we threw our stuff out there was not to drive, again, here's Lockheed, like, here's what we're going to do. No. It's more, let's start talking about real, actual implementation, and everyone can find where they are in that. But if we don't communicate and do that, there'll be random acts of engineering.
Yes, exactly.
That won't plug together or get us to an end game. All right, Kate.
I guess shifting the urgency to now from the long term, from these end users and the ultimate adopters of these technologies.
That was in metrics. That was 13.
Yeah, it was not 5. It was not 5.
Five
That's
words
what keeps
in
me
metric.
up at night. So
100% agree with you on that. All right, Jake.
Policy and regulation. I think we touched on it before, but policy and regulation.
Yep, that's right. Okay, and then we've got 2 minutes and, oh, okay. It just sat there on 2 minutes and 3 seconds for a long time. I was waiting for it to go to 2:02, and now it just jumped down to 1:56. I'm very freaked out over here. Biggest question for everybody was, beyond evident benefits like science and so forth, what do you see as the value to the average Earthling for what we're doing here? And so what, that could be what got you into it, you personally, or how do you see this impacting beneficially the people of Earth from around the world? Lori.
Inspiration. I don't
You
know
can
if
use
we're
more than 5 words, by the way. Yeah.
like probably 90% of the people in this room watched the launch on Sunday, and that's just inspiring. And people I didn't even think were connected to the space community were messaging me, like going, "What is this crazy thing?" Their kids now want to do engineering. So there's obviously an inspiration aspect to it.
Absolutely, Roberto.
I think the one point will be to learn how to live in outer worlds. That I think it is important in view of our future.
Yeah, I think sustainability. So not just creating more sustainable space exploration, but creating more sustainable energy sources on Earth, because nuclear in space is good for building out more nuclear on Earth, which we certainly need to meet our climate goals.
So you beat me to it. So I'll add one extra, and I think it's collaboration, international collaboration, to deliver the kind of the vision that we've put forward. It's going to be more than one company, more than one country. It's going to really require international collaboration, and that is a good thing.
I would say space exploration is the greatest team sport ever, even better than soccer or football. So thank you. All right. 0, perfect. Thank you so much for joining us today. Come by all the booths and talk to the teams and share your thoughts on what you see that future looks like and how you'll be part of all that. So thank you very much.